Welcome to ScienceCover.com. Let's start with the Do Now task. Pause the video and use the code to work out what the two sentences say. Today, we will look at infrared. What is the infrared? What are the uses of infrared? The relationship between heat and wavelength. Emitting and absorbing infrared light. This is the Sun. The Sun is 151 million kilometers away. It takes light traveling at 300 million meters per second, 8 minutes and 20 seconds to reach the Earth. This means we see the Sun as it was, almost 8.5 minutes into the past. We are looking back in time. But the Sun doesn't only provide us with light. Without its heat, there would be no life on Earth. So how does this heat get to the Earth? Space is a vacuum, so has no particles. This means that conduction and convection can play no part in transmitting heat to the Earth. The answer to this question is within the Sun's light. The Sun doesn't just give off visible light. It gives off a range of types of light. One of these is called infrared, and it cannot be seen with the naked eye. But we can feel infrared because when it is absorbed by a substance or our skin, it becomes heat. In 1800, William Herschel split white light into a spectrum using a prism. He then used a slit so that he could analyze individual colors of light and figure out which one carried the most heat. Herschel found none of the colors produced much of an effect on his thermometer, but when he studied an area just outside of the red, temperature started to climb. He had discovered infrared. Now pause the video and complete task 1. Let's look at the answers to task 1. Part A, complete the sentences. Infrared is a type of light. It has a longer wavelength than visible light. The infrared was discovered by William Herschel in 1800 when his thermometer detected temperature rises next to the red of the prism spectrum. Herschel proved that infrared carries heat, which we can detect when it is absorbed by our skin. So the missing words are light, wavelength, thermometer, spectrum, and skin. Part B, true or false? Infrared is a type of sound wave. False. Infrared has a shorter wavelength than visible light. False. Infrared is felt as warmth when absorbed by the skin. True. Infrared moves at the speed of light. True. Infrared carries thermal energy. True. Let's look at the uses of infrared light. Remote controls use infrared light to transmit signals. This light is not visible to the naked eye, but we can see it if we use a digital camera. Fiber optic cables are cables made out of glass that carry signals using light. Visible light is absorbed by the glass and so can only travel a short distance. We use visible light for decorative purposes. However, infrared waves do not get absorbed by the glass and can carry the information much further. We use these cables and infrared light to carry high-speed broadband internet signals. Now pause the video and complete task 2. Let's check our answers to task 2. 2 uses of infrared light. Number 1, remote controls. Number 2, communication through optical fiber. Part B. Why do we use infrared light rather than visible light to carry signals through optical fiber? Visible light is absorbed as it passes through the glass, but infrared does not get absorbed as it moves through the glass. Part C. What benefit might there be to using optical fiber as opposed to satellites? Faster, as the signal does not have to go to space and back. There's no atmospheric interference or distortions. It's easier to repair, and it's less expensive to set up. All objects emit infrared radiation, but warmer objects will give off more infrared radiation. In this picture, the red is showing areas that give off a lot of infrared radiation, whereas the blue colors are cooler and are giving off far less infrared radiation. This graph shows the amount of light against the wavelength of light. Now, we can only see a certain wavelength of light, so I'm going to mark on a region that's going to represent what we'll be able to see between. So that's the red light that we'll be able to see, and then the blue light that we'll be able to see, we'll mark on at this wavelength, and all the other colors that we can see, green, yellow, orange, red, they're all in between these two lines. Now, if we take an object that is at room temperature, that object is not that hot, so it will give off very, very little light of any kind, but mostly it'll be the higher wavelengths, the infrared light that we'll be detecting at this point. But if we heat that object up, let's say we heat it to about 800 Kelvin, then what will happen is we won't be getting very much high wavelength light coming off, but we will start then to see a peak within the infrared range. So this peak is not in the visible spectrum, it's outside of the visible spectrum, but you can see there's a higher line on the red line than there is on the blue line. Now that's our visible light that we can see. So this object is actually giving off enough red light for us to see, which means that it'll appear to glow red hot. Now this is why when we heat things up to about 800 Kelvin, we start to see them glow red hot. So when you heat iron up and it reaches this temperature, it will glow red, and if you pull it out of the flame for a few seconds, it will still be glowing red. It'll be producing its own light because it's giving off so much light, some of it outside of what we can see in the infrared range, but some of it inside what we can see inside the red range. Now if we keep heating it up, let's say we heat the temperature to about 2000, then this peak starts to move to lower wavelengths. So it's starting to move now towards peaking inside the visible part of the spectrum. And we've given off a lot of red light here, not so much blue, so this would be still appearing to be maybe yellowy in colour. However, we're now giving off far more light, so this would be far brighter, and also it would be giving off far more infrared, so it's far hotter than it was. And if we keep heating it up, if we keep adding energy to it, that peak itself will move within the visible light range, and that means then that we're giving off just as much blue light as we are red light. And if we're giving off just as much blue and red, then this will start to actually look white to our eyes. So this will be an object that's so hot, it's beyond red hot now, beyond yellow, it's looking white hot. So here on this graph, you can see the temperature ranges and where the peaks are actually found. So at about 500 Kelvin, infrared light is emitted, but no visible light. So we can't see an object glowing or giving off its own light at 500 Kelvin. As we start to approach 800 Kelvin, then larger amounts of infrared light are emitted, such as the red visible light. So we start to see the object glow at about 800 Kelvin. By the time you get to 3000 Kelvin, 4000 Kelvin, we've got large peaks now. So these are objects that are giving off not just a lot of infrared light, but a lot of visible light as well. So these look like they're glowing to us now. And by the time you get to 5000 Kelvin, we're getting large amounts of infrared emitted over all of the wavelengths. And what that means is that that object doesn't look red hot, it looks white hot. Now pause the video and complete task 3. Let's check our answers to task 3. What do color differences represent on an infrared camera? Differences in temperature. What happens to the amount of infrared an object emits as the temperature increases? The higher the temperature, it will emit more infrared light. Why does an object start to glow red when it reaches 800 Kelvin? At this temperature, we are emitting lots of infrared light, and the wavelengths of emitted light have started to edge into the red wavelengths of visible light. What happens to the wavelengths given off as the temperature increases? As the temperature increases, longer wavelengths of light are emitted. 200 Kelvin. Infrared will be given off, but no visible. 800 Kelvin should glow red hot. 2000 Kelvin glows yellow hot. 4000 Kelvin glows white hot. Let's have a look at emitting and absorbing infrared light. Which should you wear on a warm day? A white t-shirt or a black t-shirt? Black is a good absorber of light. White is a good reflector of light. So white should keep a person cooler. Infrared is a type of light, so the same idea can be used. If we have 3 cans and fill them with an equal amount of water, one silver, one white and one black, and then shine an infrared heat source onto the cans, which would heat faster? Black is a good absorber of light, so it should absorb infrared. The temperature should get highest. White is not as good an absorber of light, so it will stay much cooler. But silver is a really good reflector of infrared, so the temperature will be coolest with a silver can. To test which surface emits infrared best, we can use a Leslie cube. This is a cube with a black and silver surface that we fill with boiling water. We can then measure the temperature of radiation coming off each surface. When we do this, we find the black surface radiates the most heat. The silver surface radiates the least heat. So black is the best absorber and emitter of infrared, whereas silver is both the best reflector and the worst emitter of infrared. Pause the video and complete task 4. Let's have a look at the answers to task 4. Select the correct word. The surface that reflects infrared best is a silver surface. The surface that absorbs infrared best is a black surface. A silver surface is a poor emitter. A black surface is a poor absorber. Part B. Explain how we can use a Leslie cube to gather evidence to show different color surfaces radiate different amounts of infrared. Explain the findings you would expect. Place boiling water inside the Leslie cube. Use a thermometer to measure the temperature of the black, silver, and white sides of the cube. The black side will radiate more infrared and give the higher temperature than the silver or white side. Silver is a poor emitter, so will have the lowest temperature.